Okay, guys. Number one, limit as x approaches -1, f of x. That means we should be looking at what value the function is approaching as x approaches -1. Because this is a two-sided limit, like there's no plus or minus above the -1 here, that means we need to consider both what is happening from the left and the right. And I would say that as you approach -1 from the left and you approach -1 from the right, the value of the function is approaching 1. So the two-sided limit is equal to 1. So I'd say that's answer C. Number 2. Which best describes limit as x approaches 4? We can see that in the graph, as x approaches 4 from either side, the function is going to -infinity. Again, I would point out that this is a two-sided limit, which means we're obligated to think about what's happening from both sides. But on both sides, from the left and the right, the value is approaching -infinity. So I would say that the answer is C, -infinity. Number 3, which best describes limit as x approaches -infinity? Well, that means that we are looking at what happens to the value of the function as we go really far over to the left, because way over here, x is approaching -infinity. I noticed in class a lot of people were thinking that maybe they're supposed to be looking at this part of the graph. Nope, that is not x approaching -infinity. X approaching -infinity means you're going way over here to the left. And as that occurs, as you go way over to the left, we can see that the value of the function is just getting to be a bigger and bigger negative number. So I would say that the answer is -infinity. So that would be C. Number 4, which best describes limit as x approaches positive infinity of f prime? You might not have noticed that prime. What that means is we're asking what happens to the value of the derivative. In other words, what happens to the slope as x approaches infinity as you go very far off in this direction. And I think that the slope is approaching 0. So my answer would be 0, which is C. Number 5, f of x has a removable discontinuity at... a removable discontinuity is just another word for a hole. And that occurs at -1. So that would be -1. 6, f of x has a step discontinuity at... well, a step discontinuity is just another word for a jump discontinuity. They mean the same thing. And I would say that there is a jump right here at x equals 1. So step discontinuity at x equals 1. Number 7, which best describes limit as x approaches infinity of f of x. Looking at this function here, as x becomes very large, the denominator becomes really big, but the numerator is staying the same. So for large values of x, you'll have a small number over a very large number, and so this term here, the fraction, is approaching 0. But then of course you have this plus 1 here, so the overall value of the function is approaching 1. Number 8, which best describes limit as x approaches 3, f of x. Well, if I plug 3 into the function f of x, I'll obtain -2 over 0 plus 1. This term here, because I'm obtaining a non-zero number over 0, that indicates that I have some kind of vertical asymptote at that location at x equals 3. Because this is a two-sided limit, I'm obligated to figure out what's going on both sides. So to figure that out, what I should do is plug a number that is a little bit less than 3. That will tell me what's happening as I approach 3 from the left, and plug in a number a little bit bigger than 3. If I plug in a number a little bit less than 3, like 2.9, I think in that case, the numerator and denominator of this fraction will be negative. And so overall, this fraction will be approaching positive infinity as x approaches 3 from the left. You might wonder, what role is the plus 1 playing here? None. Because the value of the fraction is approaching infinity. That means as x gets closer to 3 from the left, like 2.9, 2.99, this fraction is getting really, really big in value. A million, a billion, a trillion. The plus 1 makes no difference, okay? So I would say as you approach 3 from the left, the function's going to positive infinity. If you approach 3 from the right, though, like if you plug in 3.01, then the numerator of this fraction will be negative and the denominator will be positive, which means the overall fraction will be a negative number. So then the function's approaching negative infinity. So it's approaching negative infinity from the right side, but positive infinity from the left side. And I would say perhaps the best answer is does not exist plus or minus infinity. That's not an option, so I would just choose A, which is like does not exist. If it was positive infinity from both sides, I would say B. If it were negative infinity then from both sides, then I would say it's C. But because it's positive on one side and negative on the other, I think this guy here is the best description. Number 9, which best describes limit as x approaches 3 from the right? Same question, except now we're just considering the right-hand side. The right-hand side, as we already discussed, you plug in 3.01, you get negative over positive, so that's going to negative infinity. That would be C. So that's number 9. Number 10, which best describes limit as x approaches infinity g of x? This one requires a little bit of writing. Ordinarily, what you would do is sort of just keep the fastest growing terms in the numerator and denominator of the function. However, this function is not really written in the appropriate form. What you need to do is expand, like multiply out the numerator and denominator. That will give you 4x squared plus 4x plus 1 over x squared minus 6x plus 9. As x approaches infinity, you're only going to care about this fastest growing term here, the 4x squared, over the fastest growing term in the denominator, which is x squared. The x squareds cancel, and you just get 4. That's the value of the limit. So that would be D. Number 11, which best describes limit as x approaches 3 g of x? Well, if you plug 3 into this function, you get a non-zero number over 0, which indicates that you have some kind of vertical asymptote. Because this is a two-sided limit, you're obligated to ask what's happening on either side. Because everything is squared in the numerator and denominator, no matter what you plug in, whether it's 2.1 or whether it's 2.9 or 3.1, you're going to get a positive number. So it's approaching positive infinity from both sides, so this two-sided limit is positive infinity. Number 12, limit as x approaches 5, blah, 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 equals. If you plug in 5, you'll get 0 over 0. And so that's telling you you have two options. Anytime you get 0 over 0, when you plug in a number for a limit, you can either have to simplify the expression by like factoring and canceling common factors, or you can use L'Hopital's rule, which says take the derivative of the top and the bottom and try again. Either way is fine. I think this can be factored as 2 quantity x minus 5 over x quantity x minus 5. The x minus 5's cancel, and so that just becomes 2 over x. Now when you plug in 5, you get 2/5, which is not one of the answers. What did I do wrong here? Oh, it is one of the answers. Okay, they're just over here now. Cool. Number 13. Limit as x approaches 3 of that expression is equal to, again, you should plug 3 in first. I think you get 0 over 0, which means, again, you could use L'Hopital's rule, or you could like try to simplify. This time I'll use L'Hopital's rule just for fun. Take the derivative of the top, and you get 2x minus 6. Take the derivative of the bottom, and you get 2x. Plug in 3, you get 6 minus 6 over 6, which is 0 over 6, which is 0. So apparently the value of that limit is 0. If you like, you can also do it by simplifying the expression. The numerator factors as x minus 3 times x minus 3. The denominator factors as x plus 3 times x minus 3. One of the pairs of the x minus 3's cancel, so this simplifies to x minus 3 over x plus 3. And when you plug 3 into this guy, you get 0 over 6, which is what we got last time, and that's 0. So, okay, that's showing both ways. 14, we're looking at the limit as x goes to infinity. You want to keep just the fastest growing terms. That's 2x over x squared, which simplifies to 2 over x. Now, what happens to the value of this expression as x becomes very large? It's like 2 over a million, 2 over a billion. That's a very small number, so that's approaching 0. 15, you should plug the number in first. If you plug -1 in, you'll get 0 over 0, which means you can either, again, simplify or use L'Hopital's rule. Trying to simplify this, though, is very hard. You would have to factor this numerator. That's not easy to do. So I think this is one that you pretty much have to use L'Hopital's rule, unless you're amazing at factoring. That would give you, taking the derivative of the top and the bottom, that would give you 6x squared minus 6x minus 11 over 3x squared minus 4x minus 3. If I try plugging in -1 now, hopefully I don't get 0. That would be 6 times -1 squared, which is 6, minus 6 times -1 minus 11 over 3 times -1 squared is just 3, minus 4 times -1 minus 3, which is, this is 6 plus 6, which is 12, minus 11, which is 1. This is 3 minus -4, so it's like 3 plus 4, so that's 7. Take away 3 is 4, so I think that's 1/4. 16, we are looking at the limit as x goes to infinity of this function. You should just keep the fastest growing terms, which is 2x cubed over x cubed, which simplifies to 2. That's the value of the limit at the end. 17, if you plug in 25, you get 0 over 0, which again means you can either simplify or you can use L'Hopital's rule. If you wanted to simplify, you would multiply top and bottom by the conjugate of the root expression, so the conjugate of the denominator in this case, although it's not always the denominator. So multiply top and bottom by root x plus 5. And yeah, so root x plus 5. And now if I do that, the numerator I'm going to leave alone, like I'm going to leave it in factored form, but the denominator I'm going to multiply out because it's the root expression times its conjugate. That will just become x minus 25. Now, this denominator of x minus 25 cancels with that x, with the x minus 25 in the numerator, leaving you with just root x plus 5. And if you plug 25 into that, you'll get 5 plus 5, which is 10. If you wanted to use L'Hopital's rule, you certainly could. Taking the derivative of the numerator would give you, I think, just 1. The derivative of the denominator would be 1/2 x to the -1/2. If you like, you could say that because of the negative exponent, this x to the -1/2 is going to go upstairs and become positive, like that. And, you know, dividing by 1/2 is the same thing as multiplying by 2. So it would be 2x to the 1/2, which is 2 root x. And now if I plug 25 into that, I get 2 square root 25, which is 2 times 5, which is 10. Same thing. Number 18, limit as x goes to infinity. Pretty interesting question. The denominator is getting bigger and bigger, that's pretty clear. The numerator, though, is not getting bigger and bigger. The sine function, remember, just oscillates between positive and -1. So no matter how big x becomes, the numerator, sine of x, will always be some number between positive and negative 1. In other words, it will be a pretty small number. So you have a small number in the numerator and a huge number in the denominator. Overall, the value of the fraction is approaching 0. Number 19, if you plug 0 into this thing, you get sine 0 over 0, which is 0 over 0. Yes, sine of 0 is 0. I saw a lot of people thinking it was other things. Review your trig values. So that means either simplify or you can use L'Hopital. Well, I don't know how you would simplify this. I don't think there is any way to simplify it, so you have to use L'Hopital. Taking derivatives, that would be cosine x over 1. Plug 0 into that, you get cosine 0 over 1, which is 1 over 1, which is 1. Hooray. 20. If I plug 0 into this thing, I get 0 over 0, which means, again, simplify or L'Hopital. Don't think you can simplify it, so it's L'Hopital. Taking derivatives, you got to be careful. Sine 2x is a composition, so you need the chain rule. Derivative of sine 2x is 2 cosine 2x minus, and then the derivative of 2x is, of course, just 2 all over 3x squared. If I plug 0 into that expression, I think you actually still get 0 over 0, which means we have to use L'Hopital's rule again. So I'm going to take the derivative of the top and the bottom a second time. Derivative of 2 cosine 2x is going to be negative 2 sine 2x, but then because of the chain rule and this inside function of 2x, we actually get another factor of 2 there, which will make this a negative 4 right there, over derivative of the bottom is 6x. If I plug 0 into that, my god, I still get 0 over 0, so I'm going to do L'Hopital's rule one more time. If I take the derivative of the numerator, again because of the chain rule, I get yet another factor of 2. And so I have a negative 8 cosine 2x over 6. If I plug in 0 into that, finally I get negative 8 over 6, which is negative 4/3, which is hopefully one of the answers. Yeah, there it is. Okay, yeah, 21. These are going to take a minute to explain. The intermediate value theorem, what does it say? Well, intermediate value theorem says basically if the function is continuous, then it takes on every intermediate y value. Okay. I don't think I want to explain this in too much detail. Basically, you need to look at what the theorem says and just memorize it or understand it. Like, I don't think I want to explain the whole intermediate value theorem from scratch. Look at your notes if you're really curious. I think looks like D is the right answer to me. No, that's wrong. D is not right. E. If n is a number between f of a and f of b, then there's a number c in the interval a to b with f of c equal to n. What that's saying is if n is an intermediate value, like an intermediate y value, then the theorem basically says the function will take on that intermediate value at some moment c between a and b. At some moment, the function will equal to that intermediate value. 22, what does the mean value theorem say? Roughly speaking, mean value theorem says that assuming the function is, continuous and differentiable, strictly speaking, needs to be continuous in the closed interval, differentiable in the open interval. The theorem says that if it meets those conditions, then whatever the average rate of change is of the function or the interval, its derivative will equal that number at some moment on the interval. Just glancing at the options without reading them closely, C looks pretty good because this right here is the formula for the average rate of change. And so this is saying there is a point C, so like there's a moment in time at which the derivative, that's the instantaneous rate of change, equals the average rate of change. Yeah, so roughly speaking, mean value theorem, if you want to say it in like one sentence, it's that average rate of change equals instantaneous rate of change, or that at some moment the instantaneous rate of change, like the derivative, will equal the average rate of change. 23, we got some table values. I guess I need to expand my window here. The best estimate for f prime of 1.25 is, I don't love this question because I think really you could perhaps like do a few different things. I mean, these are, in case it's not clear, these are values of f. When it says y, these are values of f. And so if you want to approximate f prime of 1.25, what you want to do is the average rate of change over some interval containing 1.25. Now, strictly speaking, there's more than one such interval. Like you could do the AROC from 1 to 1.25, like this, like the first two rows, or you could do from here to here, like that's mathematically valid. Probably though, they expect you to use an interval which has 1.25 as its midpoint. That's kind of the ideal, even though it's not mathematically invalid to do the other options. So I'm going to compute the average rate of change over the interval containing 1.25 as its midpoint. So I'm going to do the average rate of change from 1 to 1.5. So that would be 6 minus 4 divided by 1.5 minus 1. So that's 2 over 0.5, which is 4. So I would guess that it's 4. Okay, 24, the best estimate for f prime of 1.375. I like that question more because it is less ambiguous. Like, there's really just one obvious choice of intervals to use for that one. It's this one, right? Like 1.375 is inside that interval, and that's the smallest interval that you can use. Yeah, so you're just going to do the average rate of change of the function. Sorry, I should type 24. I'm trying to type the numbers as I go. For 24, you should just do the average rate of change over this interval because that's the interval which contains 1.375. 25, the value of m2 when approximating this integral is, okay, so we want to do m2 for the integral from 1 to 2. Well, if you're going to do m2, that means, you want to break your interval of, let's say that the interval is going from 1 to 2. Let's say you have your number line like this. If you want to do m2, that means you're breaking this up into 2 equal subintervals. So I would expect you to break it up at 1.5. So your first subinterval goes from 1 to 1.5. Your second subinterval goes from 1.5 to 2. Now, of course, since you're using m2, that means you are using the midpoint of each subinterval to determine the height of your rectangle. So the width of the first rectangle, obviously the width is 0.5. The height of the first rectangle, the height is going to be determined by the value of the function at the midpoint of this subinterval, which is the value at 1.25, which is 4.5, plus the height, what's the area of this rectangle? Well, the width is again 0.5 times what is the height? The height is determined by the value of the function at the midpoint of this subinterval, which would be at 1.75. So the height would be 9.5. So whatever that comes out to be should be the answer. 26, T4. If you're going to use T4, okay, well, for the trapezoidal method, you should just do, left endpoint and right endpoint and average them, right? So if your interval is going from 1 to 2 and you're using 4 subintervals, then I think you're looking at 1 to 1.5 and then 1.5. No, that's totally wrong. 1 to 1.25 to 1.5 to 1.75 to 2. So those would be your 4 subintervals. So for the left endpoint method, what would L4 be? Well, there, the height of each rectangle is determined by the value of the function at the left endpoint. So that's 0.25 times, the first subinterval, its left endpoint is 1, so you're looking at the height there, which is 4, plus 0.25 times the value of the function at the left endpoint of the second subinterval, so that's the value at 1.25, which is 4.5, plus, and just, repeating this, 0.25 times 6 plus 0.25 times 9.5. So whatever that is. People were asking me, how are you supposed to do that without a calculator? One thing you could do is you could say, look, the 0.25 is like a common factor in all of these. Instead of multiplying 0.25 to all of these and adding, just factor out the 0.25, and then you've got this. And that's actually quite a lot easier to do, because this number in parentheses is going to be a whole number, and then the 0.25 is just dividing by 4. So you could do that without a calculator. I'm not going to do it because I don't need to do arithmetic for you. You can do that on your own. What is R4? Same deal, except now you're going to be looking at the value of the function at the right endpoint, right? So that's going to be 0.25 times the value of the function at the right endpoint of the first subinterval. So that's 4.5 plus 0.25 times the value of the function at the right endpoint of the second subinterval. So that would be the value at 1 point. So that's 6 plus 0.25 times 9.5 plus 0.25 times 10. And so T4 would, of course, just be the average of those two. So L4 plus R4 divided by 2. Okay. 27. What is this limit? This is a derivative in disguise. You want to compare this thing to the second limit definition of the derivative, which looks like this. Oh, let me say this. So it's f prime of c equals limit as h approaches 0, f of c plus h minus f of c all over h. Yeah, compare those two expressions. What you need to do is you need to say, oh boy, those two limits sure do look the same. Oh wait, did I miss something? Oh, I wrote 26 twice. That's what it is. Okay, this is number 27. My bad. Yeah, so you're supposed to compare this limit with the limit definition of the derivative, the second limit definition, and you're supposed to be like, oh, this formula is just computing the derivative of some function at some point. So you're supposed to compare this expression with this one. I think it's pretty clear that the value of c is 3. Maybe somewhat harder is, what is the function here? Well, like the function is the function that's being applied to c plus h. So what function is being applied to 3 plus h? Well, it's x to the 4th, right? So I think it's x to the 4th. So this thing is computing the derivative of this function at this point. The problem doesn't actually ask you to find this limit, but like if you wanted to actually find the limit, you would just take the derivative of this function and plug in 3. So it'd be like 4x to a third, but plug 3 into that. I think in the next problem we actually do that. Yeah, this guy here is another problem like that. It's a derivative in disguise. This is computing the derivative of tangent at pi over 3. Oh, sorry, so 28. So this is computing the derivative of tangent at pi over 3. The derivative of tangent is secant squared, so the value of this limit is just secant squared pi over 3. And what is that? Yeah, I mean, I don't know my secant values, and neither do you. Nobody does. You don't have to know them. You just need to know that secant is the reciprocal of cosine, so this really just means cosine squared of pi over 3. Cosine of pi over 3 is a half, so it's like 1 over 1/2 quantity squared. So that's like 1 over a 4th, which is 4th, the end. You could also do L'Hopital on this guy. You could do L'Hopital. But you gotta watch out because, when you're taking, like, the derivative of the bottom is obviously 1. The derivative of the numerator is not, well, the derivative of the numerator is trickier. Like, if you took the derivative, okay, derivative of the bottom is 1. Derivative of this first term, technically that's a composition. Like, so you need the chain rule. It'd be secant squared pi over 3 plus w times the derivative of the inside function, but the derivative of the inside function is 1, so whatever. The thing that people are going to screw up if they try to use L'Hopital's rule on this is they're going to think that like the derivative of this is like secant squared pi over 3 or something. It's not. The derivative of this is 0. It's a number. Like tangent pi over 3 is a constant, and its derivative is 0. So in fact, this is the derivative of the numerator and denominator. And if you plug 0 into that, then you get, well, just secant squared of pi over 3, which is exactly what I said up here. So either way. Just, yeah, like derivative of tangent pi over 3 is not like secant squared pi over 3. It's just like, what's the derivative of pi cubed? It's not 3 pi squared. Pi cubed is just a constant. Its derivative is 0. There's no w in that expression. Okay, 29. This just means find the derivative and plug in 3. That's all that means. So I would rewrite this. I would say this is x squared plus x to the negative 1. So therefore the derivative is 2x minus x to the negative 2. If you plug 3 into that, you get 2 times 3 minus 3 to the negative 2. So that would be 6 minus 1/9. So are they're doing mixed numbers here? Oh my god. I guess that's nice of them to do that, but don't you ever write a mixed number in this class. Yeah, 5 and 8/9. Yeah, would be the value of that. Number 30. If f of x equals cosine of x minus sine of x, then f prime of x is what? They just want you to find the derivative of this function. Yeah, I mean, derivative of cosine is negative sine, and the derivative of sine is cosine, so, but there's already a minus sign here, so it would be negative sine minus cosine. Yeah, there it is. Okay, 31 through 33. All right, we're considering a bunch of statements. One is that the two-sided limit, notice that's a two-sided limit, exists. 2 is that the function's continuous at c, and 3 is that f of x is differentiable at c. Which statements are true for c is equal to negative 2? Okay, so let me look at negative 2. Does the two-sided limit exist? Yeah, because it's the same value as you approach from either side, so 1 is true. Is the function continuous at negative 2? No, like there's a hole. Is it differentiable there? No, because, like, remember, differentiability requires continuity. If it's not continuous, it can't be differentiable. So I would say just 1 for negative 2. 32, which statements are true for c equals 2? Does the two-sided limit exist? No. Like, you're getting different values as you approach from either side. So the two-sided limit does not exist, which means it's not continuous, right? It's obviously not continuous there, and that in turn means that it's not differentiable either, so none of them are true. How about 4? Does the two-sided limit exist? Yeah, you're getting the same value as you approach from either side. Is it continuous there? I think so. It looks continuous. Is it differentiable? No, because you have a corner. The slopes don't match. 34. Sorry, so that was really fast. 34. Find the slope of the tangent line. Yeah, that just means find the derivative at 9. So you're just going to take the derivative and plug in 9, okay? So negative root x is like negative x to the 1/2. So f prime of x is equal to negative 1/2 x to the negative 1/2, which is like negative 1 over 2 root x. So if you plug 9 into that, I think you're going to get negative 1 over 2 root 9, so negative 1 over 6. 35, d dx cosecant 3x. Okay. Yeah, so 35, we are taking the derivative of that function. That's all this means. We're taking the derivative. So what's the derivative? First of all, this is a composition, right? That's like cosecant of 3x. So it's a composition, so you need the chain rule. So the outside function is cosecant blank. The derivative of cosecant blank is negative cosecant blank cotangent blank. 3x goes inside both those blanks, but then we also have to multiply by the derivative of the inside function, which is 3. So there's the derivative. Oh god, Billy's doing stuff. What's Billy up to? 36. Okay, what is this a graph of? It's a graph of the velocity. Okay, so when is Billy walking left? They mean walking towards the left. Moving towards the left just means velocity is negative. So when is velocity negative? Well, this is a graph of velocity. So right in here, that's when the velocity is negative. When is Billy 37. When is Billy speeding up? Well, there's a couple ways of seeing that. You could say speeding up means velocity and acceleration have the same sign. This is a graph of the velocity. The acceleration is the derivative of velocity, so acceleration is just the slope of this guy. So, like right here, for example, the velocity is positive, but the slope is negative, so he would be slowing down here. On this region, the velocity is constant. He's neither speeding up nor slowing down. And so you can look and see when they have the same sign, but I just think it's obvious from the graph. Like, when is he speeding up? Well, this is a graph of his velocity. He's going 4 miles per hour, then he's going 3 miles per hour, then he's going 2 miles per hour, then he's going... That's slowing down. Okay, but look at this region. He's going -1 mile an hour, -2 miles an hour, -3 miles an hour. The negativity of the velocity is just telling you that he's moving to the left. Like, it's 1 mile per hour to the left, then 2 miles per hour to the left, then 3 miles per hour to the left. That's speeding up. That's speeding up. And then here, like, his velocity is getting closer to zero. Like, so that's slowing down. And then here it's speeding up. 38. What is the distance Billy traveled in the first 9 seconds? That sounds like they're asking for distance traveled, right? So I think that what you want to do is find the... Sorry. Yeah, so what you want to do is you want to... you could think of it like this. You could say to yourself, oh, distance traveled, from 0 to 9 would be the integral from 0 to 9 of the velocity function in absolute value. Like, that's true. Another way of thinking of it is just, integrating the absolute value of v just means you're finding all these areas, but you're treating them all as positive because it's the absolute value. So you're going to find this area, and this area, but you're going to make them all positive, add them up. That's the distance traveled. 39 is like almost the same thing as 38, except for displacement. Displacement is just, the integral of the regular velocity function, not an absolute value, which means this region below the x-axis you actually are going to treat as negative. So find this area, find this area, find this area, but consider this one negative and add them up. That'll give you the displacement. Number 40, where on the number line is Billy after 5 seconds? Yeah, you can't figure that out because you would need to know where he started or something. Like, you can figure out the displacement from 0 to 5 if you wanted. Like, if you integrated from 0 to 5 just by looking at this area right here, yeah, that displacement would tell you how far left he moved or how far right he moved. But you can't figure out where he is after the 5 seconds unless you knew where he started. So yeah, you need to know where he started. So that's number 40, cannot be determined. 41, you're just taking the derivative. If you're a psycho, you can do the quotient rule, but I think that's a bad idea. I think it's better to just rewrite this as 2x minus 3 to the negative 3. And then it's just sort of a chain rule thing. So you get negative 3 quantity 2x minus 3 to the negative 4 times the derivative of the inside function, which is 2. So I think that's negative 6 over 2x minus 3 to the 4th. Yeah, there it is. 42. Here's a graph of Billy doing stuff. What is this? A graph of... Oh, the position function. I don't know why they call it S of t. That's kind of weird. But, okay, this is a graph of position. After 42 seconds, after 3 seconds, Billy is doing what? Where is he and in which direction is he moving? Well, at 3 seconds, his position is positive and his velocity is negative. So, his position is positive. That means he's to the right of 0, like he's located to the right of 0. But since his velocity is negative, the velocity is negative because that's the slope, right? It's the derivative of this function. And so velocity being negative tells me he's moving to the left. So he's located to the right of 0, and he's moving left. Number 43. After 7 seconds, Billy is, it's asking about which direction he's moving and whether he's speeding up or slowing down. So if we look at 7 seconds, to me, it looks like the velocity, which is the derivative of this function, the velocity is positive, right? Which means he's moving to the right. Okay, so that's either A or B. So is he speeding up or slowing down? Well, speeding up or slowing down is about whether velocity and acceleration have the same sign. If they have the same sign, that's speeding up. If they have opposite signs, that's slowing down. Um, so I can tell the velocity is positive at 7 because the slope is 7. The acceleration, which is the second derivative, I know that the second derivative is positive here because this function's concave up. It's like a smiley face, right? So it's concave up here. So velocity's positive, acceleration's also positive, so that means he's speeding up. 44 d dx, yeah, you got to use the product rule on this, right? X times sine x squared is a product rule, but there's also a composition because of the sine of x squared. So I'd say it's like derivative of x is 1 times sine of x squared left alone, plus leave the x alone, take the derivative of the sine x squared, but that requires the chain rule. You get cosine x squared times the derivative of the inside function, which is 2x, so that's sine x squared, plus 2x squared cosine of x squared. Yeah. 45. At time t equals 0, a tiny ant starts walking on a number line with position function blah blah blah. Time is measured in seconds, and each unit on the number line represents 1 foot. Which describes the ant after 1 second? The ant is standing to the left, walking right. Yeah, well, I mean, what I would do to figure out whether the ant is to the left or the right of 0 at 1 second, that just means is the position function positive or negative at 1 second. So x of 1 is 1 minus 8 minus 9, right? Which is negative 16, right? Well, it's negative at any rate. So the ant is definitely on the left of the origin, to the left of 0. But now, in which direction is he walking? Well, that's determined by the sign of the velocity, right? So the velocity function would be 2t minus 8. If I plug 1 into that, I get 2 minus 8, which is negative 6. Okay, velocity is negative, which means he's walking to the left. 46. On what time intervals is the ant moving left? Remember, he doesn't start moving until t equals 0. So it's asking when is he moving towards the left. That's basically asking when is the velocity negative. So you need to do a sign analysis for the velocity function. I've already got the velocity function here. It's just the derivative of the position. So the way that you do a sign analysis is you ask, where is my function equal to 0 and where is it undefined? And those are the numbers that you put on your number line. This function's never undefined. So just set it equal to 0, you'll get the solution t is equal to 4. So on your number line, you just got the 4. I guess they sort of emphasize that he doesn't start moving to t equals 0, so I guess we're just sort of considering, like the universe begins at 0. And then, so what's going on? If you pick a test point, like, I don't know, 1 or something, and plug it into the velocity function, you'll get a negative number. So velocity is negative on this region, and likewise, you can figure out it's positive there. So when is the ant moving left? That's when the velocity is negative. It's between 0 and 4, the end. 47. On what time intervals is the ant speeding up? Speeding up means velocity and acceleration have the same sign. So I've already got my sign analysis of velocity from 46, so I think I just need a sign analysis of the acceleration. So I need the acceleration function. So I'm going to take the derivative of the velocity function. Derivative of velocity function is actually just the constant function 2. That might be confusing because there's no t. Look, that acceleration function is just constantly equal to 2. Like, that is a function which is always positive. Like, there's no numbers to put on your number line because this function is never equal to 0. There's essentially one giant interval. It's just always positive, right? So anyway, so speeding up means velocity and acceleration have the same sign. that would be 4 and beyond, right? Because for 4 and beyond, the velocity and acceleration have the same sign. 48. 48. What was the ant's displacement in the first 5 seconds of travel? For that, displacement, we did displacement, and you might be thinking, oh, I'm supposed to do like the integral from 0 to 5 of the velocity function. Yeah, that would work, but you don't need to do that. Remember, we did displacement way before we learned what an integral even was. Displacement from 0 to 5 is just x of 5 minus x of 0. Of course, to use that, you need to know what the position function is, and we do. So like, just do x of 5 minus x of 0 with the position function, and that'll be the displacement from 0 to 5. What distance did he travel during the first 5 seconds? Well, that's much more annoying. For distance traveled, that's much more annoying. You have to figure out the intervals of one directional motion, like when is the ant moving left, when is the ant moving right. Then you've got to compute the displacement over each of those intervals, make those displacements positive, and add them together. We already have the velocity number line here from earlier. So from time 0 to 4, the ant is moving to the left. And then we're asking about how far did he go in 5 seconds. So from 4 to 5, he's traveling to the right. So I'm going to compute the displacement over those two intervals. So over the first interval, 0 to 4, the displacement is going to be x of 4 minus x of 0, okay? And you can figure out what that is. You're going to make this positive, right? You're going to take the absolute value of this thing. Just watch out. The mistake that people make with this problem, the same mistake that they always make, is they say to themselves, like, they know they're supposed to compute the displacement over this interval, but what they do is they plug these numbers into the velocity function. No. You're supposed to be plugging them into the position function, right? Displacement is x of 4, like position at 4 minus position at 0. So make sure, you use the velocity number line to determine the intervals, but you plug the numbers into the position function to actually compute displacement. So compute, this guy, that'll be, how far he traveled from 0 to 4, and then you do 4 to 5. You're just going to do, displacement over that interval, which would be this guy. Add those two things together. The end. 50. Consider the function blah 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 in an interval. The intermediate value theorem guarantees that. I think what I want to do is look at the value of the function at 0 and at 2. F of 0 is equal to 3. F of 2 is equal to, 4 plus 8 is 12, which is 15. Okay, so like basically, if you pick any y value, like any intermediate y value between 3 and 15, I know the function will take on that y value at some moment between 0 and 15. So like, there's a point C at which the interval in which the function is equal to 5. Yeah, that's guaranteed because 5 is between 3 and 15. 2, no, because it's not between those numbers. 0, this is not even talking about the right thing. This is talking about f prime. Intermediate value theorem says nothing about f prime, so forget about these. Okay. And then I think I'm going to stop here.